To begin, here are some examples of rational functions and their graphs. And while all of these functions look very different from one another, they have some commonalities, some similarities. And those are, some of them have vertical asymptotes, some of them have horizontal asymptotes. We have oblique or slant asymptotes. We also have x-intercepts and y-intercepts. And we're going to find many of those characteristics in these next few slides. Graphing rational functions, the six-step approach. We've already said that rational functions are functions of the form f of x equals g of x divided by h of x, where h of x does not equal to 0. So to graph functions of this form, we must find a series of information. First, find the domain. Before you factor, set the denominator equal to 0 and solve for x. Exclude these x values from your domain. So to find the domain of f of x equals, our numerator is x squared minus 2x minus 3, and our denominator is x squared plus 5x plus 6. And then write the answer in interval notation. So before we factor, set the denominator equal to 0. So this will be x squared plus 5x plus 6 equals 0. And we can factor this to be x plus 2 multiplied by x plus 3. And that still equals 0. Now setting each of those factors equal to 0, x plus 2 equals 0 and x plus 3 equals 0, we find that x equals negative 2 and negative 3 respectively. Now, because we do not want our denominator to be equal to 0, I'm going to go through here and change all of my equal signs to not equal. Now, that means that x cannot be equal to negative 2 or negative 3. I'm going to write that in interval notation. My domain is minus infinity to minus 3, not including minus 3, so we use a parenthesis for both of those. Unioned with the interval minus 3 to minus 2, again, parentheses on both of those. Unioned with the interval minus 2 to positive infinity. And that's our domain, because that is all real numbers except for the values that make our denominator 0. Negative 2 and negative 3. So we're not including negative 3, not including negative 2. Step 2, find the x-intercept, or x-intercepts. After you factor and cancel, set the numerator equal to 0 and solve for x. Now notice this is the same function. So we've already factored the denominator as x plus 2 and x plus 3. And our numerator will factor as x minus 3 and x plus 1. Now there are no factors that cancel, but if some factors cancel, that actually tells you what are called removable discontinuities, or holes in your graph. But since nothing cancels, we are going to look at our numerator and set it equal to 0. Now the x minus 3 quantity multiplied by the quantity x plus 1, and that equals 0. Which tells us that x minus 3 equals 0, or x plus 1 equals 0, which means that x equals 3, or x equals minus 1. So those are our x-intercepts. We have the x-intercepts of 3, 0, and minus 1, 0. Again, x-intercepts are based off of our numerator. However, our domain and vertical asymptotes are based off of our denominator. Keep that in mind. Step 3, find the y-intercept. So let x equal 0 and then find y. We often write this as finding or determining f of 0. So f of 0 would be 0 squared minus 2 times 0 minus 3, all divided by this quantity. Let's change that to a plus 6. 0 squared plus 5 times 0 plus 6. Because our function is numerator x squared minus 2x minus 3, and our denominator is x squared plus 5x plus 6 still. Now if we evaluate those, the numerator becomes negative 3, and the denominator equals positive 6, which reduces to minus 1/2. So that our y-intercept is the point 0 minus 1/2 in this form. For our fourth step, we will determine a few different asymptotes. Asymptotes are imaginary lines. We draw them with dotted lines that the graph approaches and gets very close to. Vertical asymptotes cannot be crossed, but a graph may actually touch or cross a horizontal asymptote. To find vertical asymptotes, after you factor and cancel, set the denominator equal to 0 and solve. Now, let's just rewrite this. This function, x squared minus 2x minus 3 is a numerator, divided by the denominator, x squared plus 5x plus 6, factored as x minus 3 and x plus 1 as the numerator, and our denominator was x plus 2 and x plus 3. Now, because our denominator is equal to 0 when x equals minus 2, or when x equals minus 3, and no factors cancel, these are our vertical asymptotes. X equals negative 2 and x equals negative 3. Two vertical lines. Part 5. To find horizontal asymptotes, compare the degree of the denominator with the degree of the numerator. You want to revisit these facts over and over again until they're ingrained in your mind. If the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then our horizontal asymptote is at y equals, and we'll divide the leading coefficient of the numerator by the leading coefficient of the denominator. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And we have to move on to step 6 and look for oblique or slant asymptotes. So this function, same function, f of x equals numerator x squared minus 2x minus 3 divided by our denominator x squared plus 5x plus 6. With this, the degree of the numerator is 2. It is an x squared. That's the highest exponent. The denominator has a highest exponent of 2 as well. Because these two are equal, the degree of the numerator equals the degree of the denominator, we have a horizontal asymptote at y equals, and we'll take our leading coefficients, which are a 1x squared and a 1x squared, so we'll take 1 divided by 1, which is 1. So we have a horizontal asymptote at y equals 1. The last step, find the oblique or slant asymptotes. This only occurs if the denominator, or the degree of the numerator, is greater than the degree of the denominator. If that's the case, we will divide by long division, and whatever our quotient is, it will be in the form of y equals mx plus b. So the question is, does our function f of x equals numerator x squared minus 2x minus 3, with a denominator of x squared plus 5x plus 6, does it have an oblique asymptote? If so, what is it? If not, why doesn't it? Well, if we do long division with this, we actually will end up with 1 as a slant asymptote, which is it's a horizontal line. But that is our y, or that is our the y value of our horizontal asymptote. The reason that we don't have a slant asymptote is because the degree of our numerator is not greater than the degree of our denominator. So let's say this. The degree of the numerator is equal to the degree of the denominator. That's why we do not have an oblique asymptote in this question with this function.